Welcome back to ECE 320A. Now the semester really starts. We're in our second half. You have another exam right before the Thanksgiving break. We have 3 homework assignments prior to that. The first one is due a week from yesterday, I believe. So that's due Sunday, the 1st of November, and that will be dealing with material that we're talking about today, and you already have a good feel for that, I hope. But now we are going to talk about how to perform that S-domain circuit analysis in today's class. We're going to try to motivate that and go through an example, and then we will account for the initial conditions on our energy storage devices, the L's and the C's. And how do we incorporate those into our circuit as we sketch our circuit, and then we can then solve our circuit or system with sources and ICs built in. Here's the motivation. Suppose that I give you this circuit and ask you to find the voltage V sub 2 of t. And that's V sub 2 as a function of time. And after the exam, it looks like everyone's fairly comfortable with stating some of the characteristics about this circuit. What's the order of that circuit? Second order, because we have 2 energy storage devices. And it will depend on these values of the R's and the L's and the C's as to where those 2 poles might be, whether they're 2 real poles or 2 complex conjugate poles. Where are the poles going to be in this circuit? Can you say right half plane, imaginary axis, or left half plane just by seeing this circuit? If somebody gave that question to you on an interview, could you tell them, is this circuit stable? Are the poles in the left half plane? That's an equivalent question. Can you make that statement now without knowing any values on the R's, L's, and C's? Yes, is one very confident response in the front row, and everyone else was just still enjoying their weekend. Where did the yes come from? Oh, yes, okay, from the front right corner as the students see it of the classroom. So that's, in your view, that's sort of in the right half plane. Okay. So for me, that's in the left half plane, and that's where they actually are. Now, how can we say that? I'm assuming that R's, L's, and C's are positive. And this is a passive circuit. By passive circuit, I mean we do not have any active circuit elements. There's no op-amps in that device. There's just passive elements. You don't have to energize a capacitor to make it work. You don't have to energize with an external source the inductor to make it work. It just naturally works as a 2-element device, as are the resistors. And those resistors do what? They absorb energy. And if we just had the L and the C, then you might have a pure oscillator. You would have a pure oscillator if you just had L's and C's and no resistance. But physically, you're going to have some resistance even in the L and the C themselves as a circuit element. But here, the L and the C might put you on the imaginary axis. The R's put you in to have damping. This is a passive circuit that's stable. And you know that if you say, well, if somebody says, is this circuit stable? And you could say, yes, as long as you're not allowing negative resistors. Okay, so that could be your answer. But if you had to solve this based on what you know today, you might start writing differential equations for that circuit. or integral differential equations. And if you started, and a lot of times we happily want to write mesh equations, if we wrote two mesh equations, we might have a second mesh, a current I sub 2 in that second mesh. If we know that current as a function of time, then we can immediately write down what the voltage is across that second resistor, R2. V sub 2 of t is just R sub 2, I sub 2. Are there questions on how you might approach that circuit? Based on what you can solve that based on what you know today. It's just now we are going to try to step out of solving differential equations explicitly and essentially do those implicitly by working in the frequency domain directly, and at the end inverse Laplace transforming to get us back into the time domain. What we want to do is rewrite that circuit or draw that circuit in the S domain immediately, and now we no longer have to start writing down differential equations. We can write our equations in the frequency domain and start solving this like you did in 220. It's just now, instead of R's, you have impedances that might be functions of S. And you'll end up with this expression in the S variable that you can now take back into the time domain by inverse Laplace transform. Let me draw then. Here is what we started with. There's our circuit. Let me redraw that in the S domain. We had a source, but now we want it in the frequency domain. Whatever V sub I of t was, we simply Laplace transform it and produce a capital V sub I of S. If that was a sinusoid, you know how to find capital V sub I of S. If it was a decaying exponential, you know what capital V sub I of S was. We had a resistor, that was R1. Then we had an inductor. We had another resistor, R sub 2. But now that inductor, we're going to give it an impedance in the frequency domain. It's now S times L. And we have another source appearing, which has a value for a source as the inductor value L times I sub L of 0 minus. We have our capacitor that was in the center branch. It now has an impedance of 1 over SC, and you should be able to see a relationship between what you were seeing in sinusoidal steady state analysis and in the S domain. In sinusoidal steady state, what was the impedance of an inductor? J omega L. What have we done now? We've generalized that. Now we're not just restricting it to being purely imaginary. We now have it as an S, where S could be sigma plus J omega times L. But we just call it SL. Likewise with our capacitor, it's now 1 over SC. We have a source. And it has now a value of V sub C of 0 minus over S. And if we're interested now still in this output voltage, solving this circuit, we could find that in terms, or in the S domain, as capital V sub 2 of S. And if you were just given this circuit, you might say, oh, let me do mesh analysis, and that would be okay. You could now have these two mesh currents. Let's call this capital I sub 1 of S, and that mesh current is I sub 2 of S. If you compare this circuit, this S-domain circuit, with the one that is physically there, this one you can build on a breadboard, Now you're trying to essentially analyze that in all of its glory, and somehow you've written down this. And you might be asking, where did these sources come from? And I think it's clear by how they are labeled, but let's just ask that question. Which is, why are their voltage sources in series with the energy storage devices? And those particular voltage sources that are now in our S-domain equivalent circuit, those are actually to account for the initial conditions on our inductor current and our capacitor voltage. And that's how those particular initial conditions are incorporated as part of those sources. Meaning, those two voltage sources are accounting or account for the initial conditions on the energy storage devices. And what we want to do is figure out how or why, where are those coming from, or how can we put those into play. And if we're dealing with L's and C's, what do you think is living or somehow going to motivate these answers to these questions? What do we typically start falling back on when we say we have an inductor or a capacitor? Yes? So if you look at that polarity, the question was, how did I account for the polarity on the inductor? And you could ask, how did I find the polarity, write down the polarity on the capacitor? That will result from what I'm going to derive. So I'm going to try to answer that question if in the following derivation. But if you now say, how do we typically start recalling facts or information about inductors and capacitors, what are the two words that I just keep saying? Eli and ice, right? So if we recall, let's just look at the capacitor for now. It's still a little bit warm in the desert, so maybe we still need some ice, so we're thinking about ice. Let's now recall the current voltage relationship associated with this capacitor, or with any capacitor. And that's ice, which says, that allows us to now write down that the current of our capacitor is proportional to the time rate of change of the voltage across that capacitor. And this is, I hope that's pretty clear that that's in the time domain. These are time domain relationships. This says if you vary the voltage across that capacitor, that then produces a current on that capacitor. Now, what if we Laplace transform that differential relationship? This is why we spent time in Chapter 12. Now we're ready for Chapter 13. And hopefully you haven't forgotten since the exam how to Laplace transform this equation. I'll do the hard part. I'll do the left side. I'll Laplace transform that current, which means I just have to hit the shift key and hit I. So I capitalize I. That's now I sub C of S. Oh, I'll just help you out. And then you have C. So I'm going to give you half of the right-hand side. What's left? Did everybody hear that? It was so clear coming through. And we are going to start learning how to filter in this class. And that's what we were doing just then, filtering all of these sources and producing a very strong signal that said SV sub C minus lowercase, and this is now in the time domain, V sub C of 0 minus. That's all just from the Laplace transform. But we can break that down into two pieces, and I hope you now start to see that the current of that capacitor in the S domain is made up of two pieces. One piece is due to the voltage, and one is due to an initial condition. So that we now have SC times V sub C of S minus C V sub C of 0 minus. Now, a lot of times it's easier, or we like to think of Ohm's law as V is equal to IR. We're generalizing that so that it's V is equal to IZ. Let's solve for V so that we can sort of see this Ohm's law relationship. If we now isolate V, the voltage, the Laplace transform of the voltage of the capacitor, we can divide everything by SC. And V and I are on opposite sides, so we have 1 over SC times I sub C of S. And if we divide, or take that last term to the other side and divide by SC, we end up with plus V sub C of 0 minus over S. And this relationship is the current voltage relationship of a capacitor in the frequency domain. And this first term, this is like Ri, except now it's Zi. This is the impedance of our capacitor, which is where the impedance of the capacitor is this 1 over Sc. There's our Z for the capacitor. And then we have this initial condition term. Meaning now that we've gone into the frequency domain, we can now accommodate for both the current voltage relationship or the impedance of our capacitor, and we can also incorporate the initial condition or the initial voltage on that capacitor, all in one relationship. This now is contained in this center branch. We now have the impedance of our capacitor, that's 1 over Sc, and we've also incorporated this voltage source, and then you can determine why that polarity is what it is based on this relationship. Now, if we needed to find the voltage of our capacitor in this circuit, it would actually be this entire voltage. It would incorporate the initial condition piece and that voltage due to the impedance. That's where that came from, that center branch. We replaced the capacitor in the time domain with its impedance in the S domain and a term due to its initial condition. if the initial condition was 0, if we had 0 initial conditions on that capacitor, what would that source become? If we now zero a voltage source, what does that mean? It now just becomes a wire, doesn't it? So we haven't disconnected anything, we've just zeroed the initial conditions. We now have 1 over SC, and that's all there is. We have 0 initial conditions, and we could continue. What happens when we take these resistors into the frequency domain? There's our time domain current voltage relationship on a resistor. What happens when we Laplace transform that? It looks exactly the same, doesn't it? We have V sub R of S. The resistance is just a constant that slides outside the Laplace transform integral if we were Laplace transforming the right-hand side. And there is now our frequency domain relationship of a resistor, which allows us then to say, if we had any resistors in our circuit, those just immediately carry over into the S-domain circuit with exactly the same value and in exactly the same location and interconnection structure. The resistor carries over, or resistors carry over, to the S-domain without any changes or unaltered. Now, what about the inductors? Now we have Eli. And Eli gives us that the voltage across that inductor is proportional to the time rate of change of the current through that inductor. And just like we did with the capacitor, we can Laplace transform that. And we have V sub L of S is equal to L times S I sub L of S minus I sub L of 0 minus, which if we combine or separate that into the two pieces, we have SL, there's our impedance of the inductor, minus L I sub L of 0 minus. Here is our impedance, and all of that with the appropriate sign. This is now automatically or immediately in the form of a voltage. This is now the term due to the initial condition. And notice that this initial condition term enters into the voltage formulation a little bit differently than the initial condition term on the capacitor. This one had the initial voltage over S. This one has the inductor times the initial condition with the change of sign. Which means then that if we look at the time domain circuit for a general inductor, we now want to take that into the frequency domain, and now we need to realize that the voltage across that inductor in the frequency domain has two pieces. One is the impedance, and the other is the initial condition. And we need to create that S-domain equivalent circuit such that this relationship of the inductor voltage is correct or has this structure. Meaning, if we now draw that in the frequency domain, we now have capital I sub L of S. Our voltage is this entire piece that incorporates both the impedance, SL, and this initial condition term, L, I sub L of 0 minus. And what we want to do, this is our frequency domain. And if we have now labeled our inductor in the time domain in this fashion, we have the current going into the positive side of our voltage. We have this passive sign convention. Now we have in our S domain, we have I sub L of S, capital I sub L of S, entering the positive terminal in the frequency domain. How do we orient the sign in that source? Suppose I said, let me just apply a KVL here. So I go through that minus, then I go here, and then all the way back to that. And maybe, suppose I just put in a polarity like that, minus plus, just for grins. Now I have minus V sub L of S. That's where I'm starting, is just above that minus terminal, plus SL times I sub L of S, minus L I sub L of 0 minus, and that's equal to 0. Which, if I solve that for V sub L of S, I now have that that's SL I sub L of S minus L I sub L of 0 minus. And is that the structure I needed? Yes. So the polarity is correct the way that I assumed it going from left to right in this diagram. If I would have made the polarity, well, maybe let me leave this in red, green, let's say I went plus to minus, then this would have been a plus sign, and I would have had a plus sign there, and that's not correct, is it? Does everybody see how to interpret the polarity of those sources in the S-domain circuit relative to the inductor and the way that you've defined the current through that inductor? Suppose now that we go back to this circuit in the S domain and we try to find V sub 2 of S. And now we're assuming we have all of these initial conditions. Did you learn in 220 how to write this down by inspection in matrix form? Yes, no, no? Pardon? Oh, okay, I'll slow down. Still on the weekend. What if we want to solve for capital V sub 2 of S? How many, if we are solving this with mesh analysis, how many equations are you going to have? 2. You have two meshes to write equations for. And we can write this first mesh. Do you see that it's minus V sub I plus R1 I1 plus 1 over SC times I1 minus I2 plus V sub C 0 minus over S. That's mesh 1. And we can write that immediately in a matrix. Mesh 2 is starting at the bottom left-hand corner minus V sub C of 0 minus plus 1 over SC times I2 minus I1 plus SLI2 minus LI sub L plus R2 I2. That we can now use to solve. So let's now solve for V sub 2. We can find I sub 2 of S, and that's just one of the mesh currents. And once we have I sub 2 of S, then we can determine V sub 2 of S from I sub 2 of S. Let's now write that down. You said I have two equations, and the two unknowns are the two mesh currents, I1 and I2. So I now know that I have an I1 of S and an I sub 2 of S. Those are my two unknowns. And I know that this matrix, I have two equations, that gives me the two rows, and I have two unknowns, that gives me the two columns. This is a square matrix, this is a 2 by 2 matrix. In the 1-1 entry, or in the upper left, all I need to do is go back to my circuit and say, since I do not have any dependent voltage sources, I can simply look at the impedances that I1, that mesh 1 touches, and write those down in the 1-1 entry. The sum of those impedances. What touches I1? R1 and 1 over SC. Let me write that down. I now have R1 plus 1 over SC. I go back to my circuit and I say I want to know, in mesh 1, are there any other mesh currents that interconnect with that mesh or touch that mesh? Are there any impedances shared by another mesh? 1 over SC is shared between those two. So that one's shared, there's only two meshes. That's shared with the other one, I2, and that gets a minus sign. Remember how we were writing that anyway to go through? So this now comes in with a minus. I now add up all the shared impedances between I1 and I2 and put those in with a negative sign. If I use the same strategy for the second row, what am I going to put into the 2-2, or the diagonal entry of that matrix? What do I need to put in the 2-2 entry of that matrix? All of the impedances touched by mesh current 2. I just sum those up. I have 1 over SC, I have SL, and I have R sub 2. That's what goes in the 2-2 entry. Those are all going to be multiplied by that second mesh current. That's now 1 over SC plus SL plus R sub 2. And what impedance is shared between mesh 2 and all the other meshes? 1 over SC, and that comes in with a negative sign. There's my impedance matrix. There's my 2 by 2 matrix. It's written in terms of S's. And your calculator can invert that symbolically if we're now solving for I1 and I2, if you have the calculator. The calculators, I guess. What goes on the right-hand side? These are all of our sources. And now what we need to do is we need to look at, let's say we're now looking at the first equation, and we say, what sources do I put in there and with what sign? Now I look at the sources that influence I1, and there are two of those, and I ask if I positively increased that source, would it make I1 bigger, more positive? So if I increased V sub I, would it make I1 bigger? If I made V sub I bigger, would it make I1 bigger? Yes. What about that initial condition term due to the capacitor? If I increase the voltage on my initial condition or increase that source, would that make I1 bigger? That's sort of impeding or resisting making I1 bigger. That now comes in with a negative sign on the right-hand side. In my first equation, I can now say, oh, capital V sub I of S was encouraging I1. The initial condition term was discouraging, and it now comes in with a minus. If we have the same thought process for I sub 2, how do those sources enter into the second row of my right-hand side? Both negative signs, both positive, one or the other. Does the capacitor initial condition source enhance, or they're both enhancing I2? If I increased both of those sources individually, they would both increase I2. They are going to come in with a positive sign. So I have a V sub C of 0 minus over S plus an L I sub L of 0 minus. And now I'm done with formulating. Those are my two equations. And those are consistent with writing two differential equations. It's just now I've already Laplace transformed and solved for the two mesh current, or put my equations in terms of these two mesh currents. I now want to solve for, let's say, I sub 2. You could invert that matrix, 2 by 2 matrix, which isn't that difficult when it's 2 by 2. The 10 by 10 might be a little more challenging on the final or the third exam. But by then you've had 3 weeks of conditioning. So you're ready. Yes? Because we usually have USC, USC is negative. Minus 1 over SC, where did that come from? In either term, right? So if we look at the top row, if we were simply writing the first mesh equation in clockwise, so this only works if you put all of your mesh currents in the same direction. They're all going clockwise to do it by inspection. But now when you come to the impedance of the capacitor, you're wanting a positive drop from top to bottom. And the way that you've sketched I1 and I2, I1 encourages that drop and I2 doesn't. So the net current going down in that capacitor is I1 minus I2, so that any piece of that expression that involves I sub 2 has a minus sign, and that's where that minus sign is coming from. Because if you multiply this out, you should get that very first mesh equation. Yes, so now in the second equation, we're doing exactly the same thing, except remember that 2, 1 entry in that matrix is multiplying I1. And if we write our equation, our mesh equation for this second mesh, we're now wanting the drop to go from bottom to top. So now we have 1 over SC times I2 minus I1. No. So the question was, where are my rows, or what's the significance of the rows? The rows, the top row corresponds to mesh 1, the bottom row corresponds to mesh 2, and both of those meshes involve I1 and I2. So we, on the top row, that was simply corresponding to writing our mesh 1 equation. The bottom row was mesh 2 equation. Question?
I think he's trying to get almost what's the significance of
So the columns are, the first column is what scales I1, and the second column scales I2. So anything that's in the second column is what I'm multiplying I2, and anything in the first column, this is on my 2 by 2 matrix, is going to be scaling I sub 1. And the top row is my first mesh, the bottom row is the second mesh. Now I want to solve this. I could invert that 2 by 2 matrix and I would then have I1 and I2 both, wouldn't I? I would have an expression, I would have this messy inverse that involves all these parameters, R's, L's, C's, and S's, and I multiply it by my source. What's another way to independently and in one sort of step solve for I sub 2? You remember your linear algebra? Are you doing linear algebra yet in 310? Still flipping coins? Still pulling red balls and black balls out of urns? No? Or out of cups or some caps? All right, I have a deck of 52 cards. Where was I? Oh, not in Vegas. My other class, I've been talking about Vegas a lot. Because we've been talking about invariant things, and we said if we start in Vegas, we stay in Vegas. It's sort of a play on that. Never mind. I'm still not... I sub 2. Do you remember Kramer's rule? All right. Kramer's rule is just a ratio of determinants. What would be the determinant of the 2 by 2 matrix? You could do that, right? It's just the diagonal terms product minus the off-diagonal terms product. Let me write that. That's now in my denominator. I have R1 plus 1 over SC, and then I add a minus 1 over SC, and a minus 1 over SC, and down in the 2 entry, add R sub 2 plus SL plus 1 over SC. You don't have to do this, but I'm just showing you how fun linear algebra can be. That's now our denominator. That will be, what would you expect to be in the denominator? You go through all of this and you end up with a fifth order equation in S downstairs. Is that correct? Is it? What do you expect? Second order. This is a second order system. So you'd expect when you get all of this math done, all this algebra in S, that you would end up with a second order denominator, 2 poles. Well, that depends on, I guess, that would be our transfer function. It really depends on what V sub I of S is, what the source is, and we are going to put that into our numerator. But this denominator just came from the impedance matrix, the left-hand 2 by 2. On the right-hand side, we're solving for I sub 2. We take our 2 by 2 matrix on the left. We want to solve for I sub 2. Instead of that second column, we replace it with our right-hand column and form the determinant of that. The first column is the same. That was R1 plus 1 over SC, and this was minus 1 over SC. Instead of the second column, we replace that or substitute the right-hand side, which was V1, capital V1 of S, minus V sub C of 0 minus over S, and V sub C of 0 minus over S plus L, I sub L of 0 minus. All right, now you know if you plug in R's, L's, and C's and a particular source, capital V sub 1 of S, you could solve this. you would have I sub 2 of S. Then to find capital V sub 2 of S, what would you do? That's just scaled by R sub 2. Whatever R sub 2 is, you scale I sub 2 and you have V sub 2. Let's do another problem. Suppose the circuit looks as follows. We have a resistor, a capacitor, an inductor, a resistor, a switch, everybody's allergic to this circuit. We have an inductor, a resistor, stay awake, V sub 1 of t, capacitor. Let me see, I'm almost lost. Here we go. We need another source here. Let's say this is 5. And let's say this is opening at t equals 0.
Yeah, let's do it.
I told you you'd want those calculators. So this is now 6 farads. That's pretty good size. There's 5. Here's 4 henries. This is an academic circuit. No physical significance, but it's... But it does help me determine your grade at the end of the semester, if you can solve this. All right, there's our circuit. Oh, I need to tell you what V sub I looks like. Let me say that V sub I of t is something before 0, and then it starts shaking after 0. So that this is now, let's say this value is 1. This is V sub 1 of t. And I'm going to say that this shaking is shaking at a frequency of 5 radians per second. And that's what V sub I of t is. And that 5, you want me to slide up a little? What's the order of this circuit? 300? We have 4 energy storage elements, don't we? So this is generically 4th order. And how could we rewrite V sub 1 of t as a formula? If I now said, what is V sub 1 of t as an expression of fundamental waveforms, how would I write that? What is it from minus infinity up to t equals 0? 1. Well, I'd know how to write that if it was 1 from 0 up to positive infinity. But what if it's going in the other direction? Will that work? A reflected unit step. U will be 1 when the argument is non-negative. When I plug in minus 3 for t, what's u of minus t? u of a minus minus 3 is u of 3. That should be 1. If I did it at minus 10 for t, it's 1. If I do it for if I do it for time t equals 6, what's u of minus 6? What's the unit step of minus 6? If the argument is negative, it's 0, isn't it? So that u of minus t gives me that negative time history value for v sub 1 of t. How do I write the second non-negative aspect of v sub 1 of t? If I just wrote that, that would say that I was shaking for all time, from minus infinity to plus infinity. And I'm not, am I? I can switch it on for non-negative time by saying, let me just scale it with the unit step, or turn it on for non-negative time. That's now my functional expression for v sub 1 of t, if I needed to write it. If somebody drew that waveform on an interview, you should be able to write that right-hand side down. And if they didn't tell you what that cosine was shaking at, I hope you could measure the period, and how's the period related to the frequency. You could now find the period, let's say from the two maxes, and then divide that into 2 pi, and that would be 5. That's now how you could physically measure that. If somebody had that on the oscilloscope, a sinusoidal waveform, and you go, oh, what's the frequency of that? You can now find those 2 maxes, find the period. Well, now the oscilloscopes just figure it for you, don't they? You don't even need a calculator. But you have that frequency. Now, how are we going to solve this? I don't know, but Tharp solved it. So now, based on today's class, the right answer is put it into the S domain, right? But this is now working for both minus time and positive time, and our S domain that we're playing with is positive time, isn't it? Non-negative time. But we can incorporate all of this negativity, all of this negative time behavior in our initial conditions of these circuit elements. Because what is happening for time less than 0? What kind of source waveform is exciting this circuit? We have a DC current source, and we have a DC voltage source. We have DC excitation. That should just energize these energy storage devices, and they should just be initialized at some initial condition right at 0. I'm not recording the grimace, right? Does everybody see that? So we can incorporate all of this history from minus infinity up to 0 in the initial conditions of our 4 energy storage devices. Let's find what those initial conditions are. Let's look at this circuit as you did on problem 10 of exam 2. What's my steady state behavior after some time horizon from minus infinity up to 0? I want to know what's happening at time t equals 0. What happens to my inductors? They're just short circuits. What happened to my capacitors? They open. We're comfortable with that approach. So let's now analyze this circuit for time negative. For t less than 0, let's re-sketch the circuit. I have 1 over here for the source. I have a resistor. This was my second capacitor, let's say. Or let me just call it 0 minus. Then I have a 2 ohm, 5 amp, eight, and here is my other capacitor. Does that look right? Correct for that circuit? I've now shorted my inductors and opened my capacitors, and this is now what I have, and I have 2 sources, and they're DC or constant sources. Now I need to label, or I need to identify where my inductor currents were. I had an inductor here. Let me label this one I sub L sub 1 of 0 minus. I have another inductor, that 3 Henry inductor. It will have some initial current. Let me make it go to the right also. Let me say that that is I sub L sub 2 of 0 minus. And if I can find those 2 blue currents and these 2 voltages, then I have my initial conditions. How can I do that? How would you solve this circuit? Or what's one way of solving this circuit? Do you see that if I look at the currents leaving or entering that node, that I would have the ability to determine, let's say, this voltage, V sub x? And if I have V sub x, then I can start solving for all of these currents, and I can also find, once I know the currents, I can start finding these voltage drops. Let me say that this is node A. Let me write KCL at A. What's the current leaving the node A and going to the left in terms of V sub x and resistors and other sources? I need to know what is my voltage drop across that 1 and 2 ohm resistor. Those I could just collect into one. That's now a 3 ohm resistor, and that voltage drop is whatever V sub x is, and that 1 on its left. And I want the current going to the left, so I'm assuming that V sub x is my more positive current, and I say V sub x minus 1 over 1 plus 2. I now have V sub x minus 1 over 1 plus 2. That's the current, red current going to the left out of node A. What's the current going down out of node A? Through the 8 ohm resistor. That's V sub x over 8. those are both leaving, and I have one current going in, and that's the 5. If I solve that for V sub x, I end up with, that's just one equation and one unknown. I have 128 over 11. Now that I know V sub x, I can solve for I sub L sub 1 of 0 minus. I sub L sub 1 of 0 minus is just 1 minus V sub x over 3. That's just the opposite of that red current that was going to the left. I now want I sub L sub 1, that's 1 minus V sub x over those two, the sum of those two resistors. And if I plug in the appropriate V sub x, which I just found, I end up with minus 39 over 11. So really that inductor current was going in the opposite direction, but I'm just going to keep it with that negative sign. And that was the same current as in the second inductor. They were the same direction. Now I need to find my voltages, capacitor voltages. I can now do this to find V sub C2 of 0. I have I sub L sub 1 of 0 minus, and I have 1. If I write KVL around that highlighted left mesh, I can now say that I have minus 1 plus I sub L sub 1 of 0 minus times 1 plus V sub C sub 1, oh no, that was 2, wasn't it? V sub C sub 2 of 0 minus equals 0. And that's one equation and one unknown. Because we already know this current is minus 39 over 11. So that V sub C sub 2 of 0 minus ends up being 50 over 11. And then we can find this or solve that KVL equation across that air gap to find V sub C1 of 0 minus. Moving in the counterclockwise direction of that blue highlight, I can now say that minus V sub C sub 1 of 0 minus plus, now I'm going in the direction of I sub L sub 2 of 0 minus through that resistor of 2 ohms, I sub L sub 2 of 0 minus times 2, and then I'm back to where I started because that was just a wire getting me back to where I started. And again, I already know what the current is. And if I now solve for V sub C sub 1 of 0 minus, I have minus 78 over 11. Now what? Now I have a third of my problem solved, don't I? I have my initial conditions, right? So that now I go back to this circuit, and what do I want to do? Well, I'm guessing what happens after time 0. That 5 amp source goes away, doesn't it? So I don't have to worry about that. And what do I have? I essentially have 3 meshes. And I'm guessing that you would prefer to do mesh analysis instead of node voltage analysis, just because this looks like three meshes staring at you. So, if we want to do mesh analysis, it's usually best to consider your initial conditions as series voltage sources. Next time, we will talk about how we can incorporate parallel current sources across our impedances for capacitors or inductors if we were doing node voltage equations. But today, we've been concentrating on series voltage sources. Let's incorporate those into this circuit. Now we want t greater than or equal to 0, and now we can go immediately into the S domain. Upstairs, we had a 5 ohm resistor. We had a capacitor that was 6 in numerical value, so we have 1 over SC, that's 1 over S6, and our source is plus minus, but we need to keep track of the sign. That was minus 78 over 11S, where that was V sub C of 0 minus over S. That's my very top branch in my S domain equivalent. Then I had an SL, which this inductor value was 3, and I had its initial condition, which is minus plus, and that was L times the initial value of that current, and that was minus 39 over 11. And I had a 2 ohm resistor. In the middle branch, I had a capacitor of size 5 farads. That's 1 over SC, or 1 over S5. I had its initial condition, which was 50 over 11, but I divide that by S, because that was V sub C of 0 over S for this source. On the far right, I had a resistor of 8. And now I can start to work on what was to the left of all of that. I had a 1 ohm resistor. I had an inductor of value L equal to 4, that's SL or 4S. I had a source minus plus of L times the initial current value. And what's the Laplace transform of my V sub 1 of t for positive time? That was a pure cosine. Do you remember how to Laplace transform a cosine? That was pretty good unison. S over S squared plus omega squared, which is 5 squared. Now, we said we were going to do mesh analysis. Let's call this mesh I1, this mesh I sub 2, and this mesh I sub 3. Now, how big is my leftmost matrix? I'm now going to write this as some matrix.
There's a question.
Let's continue. Yes, question? What happened to our current source? I was looking elsewhere. What happened to the current source? It opened up, so I just erased it. Why is my top source this one? So now when I come down here, it's going to be, how did I define my capacitor voltage? I defined it to be from minus to plus, and here, down here, I said bottom to top was minus to plus, and those should be consistent if I look at how those polarities are incorporated. Does that help? So you do have to be very careful of the polarities on your voltage sources and the direction of your currents in your current sources when you replace these initial conditions with current sources. Now, how many equations am I going to be writing? 3, because I have 3 meshes. How many unknowns do I have? I have 3 mesh currents, and those are the unknowns that I'm solving for. So if I was just writing this down just to try to get a feel for what's going on, there's my unknowns. And then I have something on the right-hand side, and what's over here? These are my sources. What is in this, and what's the size of this matrix? I had 3 equations, that gives me the 3 rows, and how many columns? The columns have to be compatible or consistent with the number of unknowns, and I had 3 unknowns. That left matrix better be square. It's 3 by 3. And what's going to go into, let's say, so if this is now my Z of S, does this make sense? Now I have Z times I giving me V. V is equal to ZI. ZI is equal to V. Now I noticed on your exams sometimes you would be writing equations and you're just trying to find equations, but sometimes you would be adding voltages and currents. You had V plus I. It's like, is that quite right? So that's a way to check your work. When you start writing an equation, you could just say, what are the units on each of these terms in my equation? Ooh, I've got a voltage, a current. Where did that? I've got something wrong here. If your equation is voltages, they should all be voltages. If they're currents, they should all be currents, and that's what we're getting here. ZI are voltages, my right-hand side better be voltages. You know what I'm tempted to do? I'm tempted to fill in the blanks after class and return your exams. Will that work? I think I've lost you.